Dok istraživanje dubokog svemira iz dana u dan napreduje, NASA u svojim centrima diljem Sjedinjenih država potiče taj proces brojnim tehnološkim inovacijama. Znanstvenici iz istraživačkog centra Glenn u Clevelandu razvijaju revolucionarnu tehnologiju za primjenu u zrakoplovstvu i svemirskim misijama. To je jedan od 10 glavnih NASA-inih centara koji su ponajprije orijentirani na osmišljavanje tehnoloških rješenja za područje zrakoplovstva i svemirskih letova. Zapošljava više od 3000 državnih službenika i vanjskih suradnika. U istraživačkom centru Glenn smješteni su testni pogon Neil Armstrong i laboratorij za istraživanje bestežinskog stanja. Oni čine jezgru NASA-inih aktivnosti na području razvoja tehnologije za istraživanje svemira.
My name's Ray Kastner. I've worked for NASA Glenn here in Cleveland, Ohio for 31 years. I started here right out of college as a test engineer. I worked in our acoustics lab. From there, I went to our jet engine facility. I'm currently the propulsion lead for NASA on the X-59 low-boom flight demonstration vehicle.
I'm Dale Van Zantia. I'm in the acoustics branch at NASA Glenn Research Center. I've been here at NASA since 1992. I actually came as a graduate student and did my graduate work here at NASA Glenn. I'm actually a farm kid from rural Iowa and grew up tinkering with machinery, but had a keen interest in science and math, and ended up going to college for mechanical engineering, where one of my professors was a specialist in gas turbine engines and really got me interested in jet engines. And that's how I actually got to NASA here, doing research on the aerodynamics of fans and compressors and jet engines.
I have been at NASA for 21 years. I work on the development of electric propulsion devices for space exploration.
I've been here for about 30 years now, and I work on a lot of things in this agency, mostly science-related in the last 15 years or so. My roles today at NASA are to first manage the science activities that our center does. And I'm also the principal investigator on what's known as LISI, which is the Long-Lived Solar System Explorer, and that's building and developing a small Venus lander.
My name is Harvey Chavez. I'm the chief of the Technology Transfer Office. Our job is to take NASA's technology, our intellectual property portfolio, and work with small entrepreneurs, startups, local industry, companies, individuals, and look to commercialize our technology.
Istraživanje svemira zahtijeva mnogo vremena, strpljivosti i testiranja. No u svakom centru koji smo posjetili, zatekli smo vrlo motivirane i odlučne timove koji poslu pristupaju s mnogo strasti. Tako je bilo i u istraživačkom centru Glenn, gdje mnogi NASA-ini stručnjaci i znanstvenici rade već nekoliko desetljeća.
Well, I actually started out in the fan and compressor group, did the aerodynamics of high-speed fans and high-speed compressors, and did that for a few years, and then actually moved over into the acoustics group in 2003.
I've worked here in Cleveland, Ohio at NASA Glenn for my whole career. The propulsion team here at NASA Glenn is actually a fairly small team. We're about 5 or 6 people, but we're part of a much larger multi-center team. On the NASA side, we have people from centers all around the country, NASA Langley, right here at NASA Glenn in Cleveland, NASA Ames, and then, of course, the Flight Test Center, NASA Armstrong, out in California.
Some of the testing and the different capabilities that we have in our wind tunnels are very unique in that there's only a few places in the world that do the kind of testing that we're able to do here.
We do a number of really exciting things, very cutting edge in terms of the technology and the exploration side, scientific discovery, so it's really amazing. It's not something I would have dreamed about or did dream about when I was younger, but certainly I'm enjoying living that dream now.
NASA technology, NASA ideas, ability to help NASA solve some of its problems or a company's problems is really a core of what we try to do in terms of working with entrepreneurs, working with small companies to help them be successful. Our success is their success is our success. We're really looking to take that company's needs, that entrepreneurial desire, that entrepreneurial spirit, and be able to spin it off into a situation, into a reality where the company is successful, where society can benefit, and where the technology can get out there and help the most number of people in the best way possible. It says in our front gate, for the benefit of all, and we really believe that's one of our maxims for why we do what we do.
U partnerstvu s NASA-om Lockheed Martin rješava jedan od najvećih problema nadzvučnog letenja, prasak koji nastaje pri probijanju zvučnog zida. Nadzvučni zrakoplov X-59, koji zbog jedinstvenog dizajna mnogo tiše probija zvučni zid, poslužit će NASA za prikupljanje podataka o reakciji javnosti. Podaci će regulatornim tijelima poslužiti kao kriterij za donošenje standarda o prihvatljivoj razini buke u civilnom zračnom prometu, kako bi se ukinula zabrana komercijalnih nadzvučnih letova iznad kopna. Time bi se na svjetskom tržištu otvorile nove mogućnosti za proizvođače zrakoplova, a putovanja bi trajala upola kraće nego danas.
I do remember that when I was a young kid, I went to the air show in Oshkosh. I got to see one of NASA's X-planes from the 1970s fly. That was the oblique wing demonstrator X-plane.
Airplanes have gotten a lot quieter over the last 5 decades, but we still have a little ways to go. So NASA has some longer-term goals for the subsonic aircraft fleet.
Since 1973, supersonic flight has been prohibited over land, and that's really what NASA's been working on for decades, actually. There's been a lot of technology that's been developed over the years to make supersonic aircraft quieter, and based on a lot of that technology, the time is right to build a low-boom flight demonstration vehicle and try to test some of these technologies that will make a supersonic aircraft quieter and able to fly over land.
The goal is to make aircraft quiet enough that they blend into the background, so that you wouldn't necessarily notice aircraft taking off and landing from airports.
Could imagine trying to fly to, like say, Cleveland to Los Angeles and being home for dinner, right? That would be great. Or you could fly to, somewhere overseas in half the time and not feel as exhausted.
What you've seen over the years, like if you go back to the late 1960s, the engines were these really tiny cigar-shaped things. They made thrust by putting air out the back at a really high velocity. Worked well, it wasn't all that efficient, and it was very noisy.
Nadzvučni letovi preobrazili bi komercijalno tržište i omogućili putnicima da mnogo prije stignu na odredište.
So currently, what NASA's doing is building a low-boom flight demonstration vehicle. The vehicle is being built under a NASA contract by the Lockheed Martin Skunk Works. It's roughly halfway through assembly, and first flight is planned for next year in 2022 with acoustic validation tests in the years following.
For subsonic aircraft, they always fly at about the same speed. We'd like to fly at high subsonic Mach numbers, so whichever engine concept we come up with is going to have to work both quietly and efficiently at that flight speed.
Low boom technology has been developed by NASA and with NASA partners, right? And it's been something that NASA's been working on for decades.
What we do here at NASA Glenn is we focus on the propulsion system, the jet engine part of the airplane. And that's what you primarily hear making noise when an aircraft takes off from the airport when it's under high power.
So there's a large team of people who've been working the supersonic technologies for decades. We have had experts working on the actual sonic boom. Sonic boom research is also more complex than just the vehicle design. It's how do people respond to sonic boom. So NASA studies that as well. NASA has facilities that people can go and listen to sonic booms as if they're outdoors or if they're indoors, and they can rate how the sonic boom might annoy them. And that's how we've come up with levels of sonic boom that would be acceptable.
NASA now talks a lot about enabling sustainable aviation. A part of sustainable aviation is very high efficiency engines and aircraft. But a piece of that is also quiet and clean. So it's really all three of those things that you want to combine together that will continue to enable the number of flights that we want to have, as well as reducing any overall impact to the community and the environment.
Being able to build a low boom vehicle is largely based on advances in computational speed and a lot of the new design tools that have been developed by NASA and NASA partners over the past few decades, but especially in the past 10 years. There's been a large focus on being able to reduce that sonic boom and develop technologies that would enable industry to build a next generation Concorde with modern technologies that would also be more fuel efficient and environmentally friendly.
Probijanje zvučnog zida pojava je izazvana udarnim valovima, koji nastaju kad se neki objekt giba brže od zvuka. Pritom nastaje golema buka, koja ljudima na tlu zvuči kao eksplozija.
Noise is created when, as one of my colleagues would say, when you push on air, you can actually create a small pressure pulse that's perceived by people as sound. Some sound is good, and sound that we don't like we call noise. If you think about an airplane, you have to generate thousands of pounds of thrust with the fan and the engine to get the airplane off the ground. You're pushing on air really hard, and that potentially creates a lot of noise. So we have to work on both methodologies for sort of how to quietly push on air, and then we also work on other noise absorbing kinds of technologies to make the aircraft engine quieter.
Here at NASA Glenn, we've worked on the jet plume and how the jet plume affects sonic boom. That was done in one of our facilities, the 1 by 1 foot supersonic wind tunnel here in Cleveland. And then more recently, we've also done wind tunnel testing for the jet engine on the X-59 to study the airflow that goes into the jet engine to make sure that it gets smooth and steady airflow for all phases of flight. And that was done right here in Cleveland at our 8 foot by 6 foot supersonic wind tunnel.
The engines you see today have these very large diameter fans on the front, and they sort of push on the air more gently, which makes them more efficient, and it also makes them much, much quieter. Over time, you can see engines just keep getting larger and larger and larger in diameter. What happens, though, is once you get to a certain size, the weight and drag of the nacelle that wraps around the fan actually begins to hurt you. So one of the sort of upcoming technology ideas is actually get rid of the nacelle from around the fan and go to these what we call unducted fans. And they're these very fancy curved high-speed propellers which are actually very, very efficient, and yet they still allow the airplane to fly at the same speed that you would fly if you were on an aircraft with a more conventional ducted engine.
The propulsion team really works as an integrated team. We've done wind tunnel testing to make sure that the engine will get smooth and steady airflow. We've also been working hard on the integration efforts with the airframe, because this is the first time that this engine will ever fly in this airframe, right? X-59 is a one-of-a-kind airplane, whereas the engine has other applications in other airplanes, but we need to make sure that it's safe and will provide power and thrust for the X-59. We are fortunate to be able to do 2 wind tunnel tests on this airplane right here in Cleveland at the 8x6. We did an aerodynamics test first to make sure that the vehicle is stable and has good aerodynamic performance. And then we actually did 2 propulsion tests. The first one showed that the airplane would get smooth airflow and be free of distortion. But then we did learn some things in the first test, so we had to bring it back for a second test with some dynamic instrumentation to be sure that there would be no dynamic distortion in the engine. And luckily, the inlet did pass, so we're confident that the engine and the inlet will be ready to fly.
For subsonic airplanes, it's really a battle between how efficient you can get the engine. You want to burn as little fuel as possible. And then can you still make it quiet enough that it makes sense and meets the regulations and doesn't disturb the communities.
And in that vehicle's mission, it's not a commercial vehicle. It's a demonstration X-plane that's going to fly around the country at selected cities that were chosen so that people can hear these low levels of sonic boom. And people will have technology to rate the sonic booms, and if they even hear them at all. And that's the hope, is that we can collect data so that the regulatory agencies can then change the rule and allow supersonic flight over land in the United States.
NASA stvara iznimno mnogo tehnologije, pa zato i surađuje s mnogim partnerima diljem svijeta koji su zainteresirani za daljnji razvoj i komercijalizaciju.
One of the missions of the office is to identify where a company or individual or an entrepreneur might see a need for a commercial solution that NASA technology would be able to assist in. Then we work with that individual, the company, the entrepreneur, etc., to develop a relationship which we hope will eventually end up with a license, a new startup, an opportunity to take NASA's technology and to be able to share it with greater portion of the public. Our goal is to help the company to be successful. And if they need a little bit of extra time, they need a little bit of extra something else, we try to make that happen. One of our recent successes is with an entrepreneurial company that's taking shape memory alloy technology that's used in some of the ideas we have for future tires that would be used on a Mars or Moon rover. And this company is looking to take that same technology and apply it to other mobility situations, like in bicycles or in mopeds or other devices. And this would be a shape memory alloy-based tire that would never go flat. It doesn't need to be, doesn't need to have any air pressure to it because it will always retain its shape. In addition, another big success we've had is with some of our aerogel technologies, which is it's the lightest material known to man. This company located up in Boston, originally also a startup, has really developed that technology and is basically using it in insulation because of its fireproof properties and using it in liners for airplanes and reducing the weight in that situation. You're also looking to use it in apparel to kind of keep you warmer for less weight and less bulk.
Istraživački centar Glenn jedinstven je, jer obuhvaća laboratorije u kojima se obavljaju simulacije i strogo testiranje tehnologije prije lansiranja u svemir.
One of the unique capabilities, infrastructure, if you will, that we have here at Glenn is our Glenn Extreme Environment Rig, which is called GEAR. And this is a facility that's uniquely capable of simulating atmospheres. We can mix in different gases, mix them in different concentrations, and expose them or put them in a state of different temperatures and pressures. So we have a broad region which we can explore and simulate. We will use GEAR to simulate the environment so that as we develop technologies, we know that they're making the measurements that we need. We know that they survive in the conditions that they have to. And then we'll use that same facility then to qualify and make sure and be very confident that what we've done will actually work. One of the phrases that we'll use to describe that is test as you fly and fly as you test. We particularly have been using that right now to simulate Venus. So Venus is a very, I would say, harsh environment. It's got high temperature, high pressures, reactive chemistry after the surface. And this GEAR chamber that I'm referring to gives us the unique ability to simulate that, and it's very precisely. Whatever we put in there, we think that it's on Venus because we're able to simulate that so accurately. And that's unique in the world in that way, to simulate the temperature, the pressure, and the precise chemistry, and sustain that over long periods of time. Venus is one that we've been simulating, but we can also do others. We've got a test that will be simulating conditions in Jupiter, for example. So we can apply it to different bodies, and as we learn more and we explore in other regions, we'll be using that in that way as well. We use the Venus chamber GEAR to simulate the conditions, and what that will do is allow us to predict, if you will, what a mission will see. So the way we answer the questions about how Venus evolved to where it is now is by sending missions and taking data in situ or remote sensing data from orbiters around Venus. So the missions themselves will produce the data for it. The way we use GEAR is to prepare the technologies, And we also use it to test the instruments so that when we see something from a lander that's on Venus or we see something from an orbiter, we'll be better able to understand what it's really seeing in that environment. So we will, for example, put in different sort of minerals. We'll put in basalts into gear and see how the chemistry interacts with that. By doing that, then when you send a lander, you'll know that I'm looking at this, but inside, this is what really is happening. And that's what gear does. It allows us to understand better what we see and prepare our mission so when they get there, they'll actually get the data that we need for the duration that we need it for. Venus is so similar to Earth in some of the key ways, such as the size, location in the solar system, but in so many other ways it's so different. And one of the things that we need to understand is why the change. What happened? Was there water? Was there an ocean? Where did it go? When did it go? All those kinds of things are really critical for us to understand terrestrial planets, tell us more about our own planet as well as the universe around us.
Zbog ekstremnih uvjeta koji vladaju u svemiru, mogućnosti leta su ograničene. Današnji potisnici dobro služe svrsi, ali zahtijevaju iznimnu preciznost pri konstrukciji i upravljanju.
My expertise is in the area of developing thrusters. We do very little with the spacecraft itself. Our devices can be integrated with many different types of spacecraft, but right now the focus is to integrate the APS thruster with the power and propulsion element that Maxar is developing for NASA. NASA Glenn, along with our colleagues at JPL, developed a prototype thruster. We call it the Technology Development Unit. We built 3 units, and those were tested extensively here at Glenn. And after 3 years or 4 years of testing and researching it and developing it and taking data on it, that technology, there was a request for proposal to actually build the flight version of that thruster, and that's the stage that we're on right now. What we're working on is development of a 12.5 kilowatt thruster that's going to be used on NASA's Gateway mission, the Artemis project. Gateway will have a power and propulsion element module that will use electric propulsion for orbit raising and orbit maintenance.
Električna propulzija nova je vrsta pogona koji se primjenjuje u svemirskim letjelicama. Umjesto kemijskih pogonskih motora pokreće ih električna energija. Za razliku od kemijskog pogona koji podrazumijeva gorivo velike mase, motori na električni pogon mnogo su lakši.
Electric propulsion devices are devices where you take electric power, and the devices I work on use solar electric power, so you use solar arrays to capture the sun's electric power, and then we convert that into kinetic energy in the thruster to provide propulsion for the spacecraft. Electric propulsion development is always continuing because the devices operate at different power levels. New devices are being invented that serve for different missions. There's different types of electric propulsion. NASA invented one type. Russians worked on the invention of the Hall thrusters. NASA did the ion thrusters. So it's been a ranging group of organizations that invented electric propulsion thrusters. As part of the development of the electric propulsion devices, extensive testing is performed before the unit is approved for flight. Long duration testing of the devices to show they have the life. There's a lot of environmental testing that's done that includes thermal vacuum testing and structural testing, which includes vibration testing and shock testing. So that's how the units are certified to be flight worthy. There's a very extensive and detailed and long testing program. The implementation of the APS thruster, the 12.5 kilowatt devices, can be used for deep space missions. They will allow you to utilize the available solar electric power more efficiently to go further. And the big benefit of the technology is that it allows you to use a lot less propellant versus chemical technology. So what it does, it reduces your launch costs significantly and reduces the size of your spacecraft.
Laboratorij ugrađen u letjelicu omogućit će NASA-inim stručnjacima da obavljaju znanstvene eksperimente dok je još u pokretu.
Our goal with the Venus chamber is to understand better the environment so when we go there we can better predict it. We also want to use that to mature our technologies so that we will have the ability to take the right measurements, to take them for the duration that we need to do that, to understand the background and the physics and all those things that are happening, and to collect all that data, and then to qualify and make sure that what we've built, that we're ready to send to Venus, can actually work. So those are our objectives. Once we've done that, we're going to continue to evolve that capability. We'll look at maybe other destinations, other planets, and just continue then to support the mission so that as we get things and we get surprises, which we always do, we'll be able to explore what's happening and again, better interpret what we've seen. On Earth here, our pressure, we would call it maybe 1 bar, right? On Venus, the surface pressure is 92 times that. So it's about being nearly a kilometer underneath the ocean. That's about how much pressure you would feel. The temperatures here on Earth, as you know, we see them are 20, 30 degrees Celsius, let's say in a given day. On Venus, it's 460 degrees Celsius. In the clouds, we have layers of sulfuric acid clouds, but down as you go deeper, then there's still some sort of reactive chemistry. The sulfuric acid itself is not on the surface, but as we go to the surface, we kind of take a little shower in the sulfuric acid clouds, but then we get down deeper and there's still reactive chemistry. So over time, the reactivity chemistry will eat away at the things that you put down there. So not only does the temperature mess with your systems and the pressure, but you also have that chemistry that will affect you as well. So those are all the different challenges, environments that we see and that we simulate and that we work to address in our work here at Glenn. So one of the other things that we hope to do with gear is to enable our systems to last much, much longer than what was done in the past. The landers that have been sent to Venus, and this was years and years ago by the Soviets, the best that any lander on Venus survived was 127 minutes. What we're aiming to do with our gear chamber is to demonstrate the system that we're developing, which is called Lizzie. The goal of Lizzie is to last for 60 days, and we have plans for other landers to last twice that much, 120 days. Just imagine trying to understand the weather on a planet if you've gone there once or twice and you've lasted 2 hours. There's so much more you're going to need to know to understand that system. You need time-based measurements, and what we're doing with gear and what we're doing with some of our high-temperature electronics and other things that we do here at Glenn allows us to make those big steps and get that data that we can't get otherwise. We're pairing our unique capabilities, the infrastructure, the gear chamber, the high-temperature electronics, the silicon carbide labs. We're pairing that capability with the people, with the challenges that are out there, and we're matching those two together to be able to make real progress, contribute to the scientific questions, contribute to the broader community, and then benefit all of us.
Iako je električni sustav propulzije učinkovitiji, brži i lakši od kemijskog, i dalje treba gorivo.
The technology that we're building, it does use xenon propellant, which has many characteristics that make it very attractive for use as propellant. But again, these units will use propellant. They expend it at a much lower rate than chemical propulsion devices. But at some point, you do have to refuel the spacecraft to be able to continue thrusting using these devices. And the lifetime of the device that we're developing, it's designed to operate for in excess of 23,000 hours at full power. So, and that generates enough delta V to allow you to complete many missions that are of interest to NASA as far as low Earth orbit for orbit raising or for deep space exploration. The state-of-the-art when we started this project was a 4.5 kilowatt device. Airjet Rocketdyne builds the XR5, which is a flight thruster that's being used by the US government and commercial companies. This device represents a 3x increase in the power level of the Hall thruster technology, and it presents at least a 2x increase in the lifetime and throughput capability of the devices. So the next step for NASA exploration after we fly this mission and we demonstrate that it meets all the requirements and all the mission goals is to actually develop a higher power device. Emission studies have shown that these devices can be used for human exploration of distant planets like Mars. The next stage is actually building like a 40 kilowatt device that can provide, when clustered with other devices, it can provide enough thrust to actually transfer cargo and humans in a relatively acceptable time duration. And that is the next goal for the development of these electric propulsion Hall thruster technology. The technology, the 12.5 kilowatt advanced APS thruster, is being used for NASA missions. But as we get more power in space, the technology will actually be used for commercial applications. And that is what the next use of that technology could be too.
Iako su NASA-ini tehnološki izumi namijenjeni ponajprije istraživanju svemira, mnogi nađu primjenu na Zemlji, pridonoseći razvoju čovječanstva.
First flight, for the experimental plane, the X-59, will be in 2022, and then there will be 3 phases of testing. There will be some airworthiness testing to make sure the vehicle is safe to fly. Then there will be some sonic boom measurements, and then finally it will go out into selected cities around the country to collect out to allow the population to hear these very low levels of new sonic boom that the new technologies have enabled.
As you can hear behind me, aircraft still are not as quiet as we would like them to be. So again, NASA's long-term goal is to keep any objectionable noise from aircraft operations to within the airport boundary. Essentially, the airplanes would blend into the background noise, and I think that would be kind of an ideal situation. We're still quite a ways from that. Airplanes would have to get substantially quieter to actually meet that goal. We're working on a variety of technologies that make the engines quieter, that actually make the airframes themselves quieter. But that's always sort of teed up against the desire for lower carbon and more efficient solutions. And higher efficiency and quieter don't always go together easily. I think if you would go ask communities around airports, they would say it's more important to make them quieter. Aviation is such an important both economic and societal impact. If you look at aerospace within the United States, it's about 5% of our gross domestic product. So that's aircraft engines, satellites, rockets, that kind of thing. So it's really a very large part of our economy, but it's also a big part of our social life and being able to travel and see family and those kinds of things. So the intent is to make it possible to continue the economic and social life without any adverse negative impact. You have to do the aerodynamics of these fans first and understand that before you can go ahead and continue and do the acoustics. It's a battle more between not adding weight or not making the airplane burn more fuel, but keeping it quiet and still maintaining the efficiency. And a lot of the methods we use these days with computational simulations have greatly increased our ability to really optimize things so that we can actually do both and kind of get the best of both worlds. Whitney geared turbofan, that particular engine fan actually came through our 9x15 wind tunnel at subscale for some of its early development. And that idea for moving into that design space came out of some NASA research actually back in the mid-1990s. So now that original idea has matured into an operational airplane engine that's out there flying around in the fleet. And we've had several of those kinds of success stories from our research, and that's what we really want to do.
Budući da stotine patenata nikad ne dođu u fazu razvoja i proizvodnje, NASA je pokrenula program suradnje sa zainteresiranim tvrtkama.
Here at the Glenn Research Center, we have well over 200 patents available for license. Across NASA, it's probably approaching 1,000. And you'll look through that patent portfolio, which is totally open to the public. You go to technology.nasa.gov. You can look through the patent portfolio. You can look through the software portfolio. And you'll find a technology that might be applicable to your need. You'll contact us. We'll develop a relationship. We'll give you a license, whether it be a research license for you to be able to play with it for a little while, a commercial license if you already have a commercialization plan, in a way to kind of take that technology from where it is today and to be able to solve the company or the entrepreneur's challenge and problem. We've had ongoing relationships with numerous entities from across the globe where we look to take that technology and apply it to new and innovative ways.
One of the things that we're really excited about is combining the technologies that we have with the unique facilities that we have, with the experience and the talent of our scientists and engineers, and be able to build a lander on the surface of Venus that lasts not 2 hours, but 60 days, 120 days on the surface of Venus, sending back data to Earth so that we can follow and understand what's happening there on that planet and get to understand it better, the systems. Why is it the way it is? Why is it different than where we are here at Earth?
NASA's Gateway project is aimed at establishing lunar presence. As part of that, NASA is developing the power and propulsion element, which will provide a permanent outpost by the moon. NASA is developing the advanced electric propulsion thrusters to provide orbit-raising capability to the Gateway to raise it from low Earth orbit to the NRHO orbit in cislunar space. Once we get to cislunar space, the advanced electric propulsion thrusters, the Hall effect thrusters, will provide the orbit maintenance for that mission.
The geared turbofan, the thought that came from some NASA research in the mid-1990s. It was matured through some additional testing here at NASA Glenn in the early 2000s, and now that is an actual operational engine out in the fleet. And so that's one of our big success stories among several within acoustics here at Glenn, and that's what we really hope for. We want to mature the technologies and get them out there flying.
NASA works aeronautics technologies in addition to the space technologies that everyone's familiar with. And certainly the hope is that we can take these design tools that I've talked about earlier and once they've been demonstrated on a vehicle like the X-59, then aircraft companies can take those design tools, actually that they've had a large part in developing themselves, but they will have been validated and they can take those design tools out and design actual commercial vehicles that you and I could fly on in the future. So there could be a next generation Concorde and we could be flying across the country in half the time or flying to other countries in half the time.
Ultimately, NASA's goal is to develop new technologies, research them, refine them, and then transition them to industry.
It's not just about Venus, right? It's about what that does for us. Scientifically, we understand our planet better, but there's also the technical parts of it. So the things that we're developing for Venus applications do have applications on other planets, Mercury and such, but also here on Earth. So these high-temperature systems are going to benefit things like the deep mining, better combustion engines, because the sensors and things we use for Venus kind of got their heritage out of combustion engine and some of the work we do in the aeronautics, but they feed back into that, right? So it's going to benefit in indirect ways as well.
Ako je dovoljno strastven, odlučan i žilav, čovjek doista može postići bilo što. S obzirom na to s koliko strasti znanstvenici i stručnjaci iz istraživačkog centra Glenn pristupaju svom poslu, uspjeh im je zajamčen.
I love my job at NASA. I love the agency because it's the people that you get to work with, great people, brilliant people, very motivated to contribute to society and to learn and explore. And then also the technologies, the capabilities, the assets, they're just incomparable, right? It's ability to play in a real sense and make a real contribution to understanding our universe and to benefiting everyone.
For me, the whole project is impressive, right? I mean, it's every engineer's dream, to work, in the lab and on analysis, and then actually see their work go onto a flight vehicle, which, like I say, I've been able to do because I started on this program doing jet plume effect on the aft end of the vehicle, and you can actually see when you look at the back of the vehicle, there's a deck that sticks out behind the nozzle, and that's technology that we had a large part in building right here in Cleveland, that actually made its way right onto the airplane.
We are very privileged here to work at NASA. We get to research new concepts, mature them to flight, and seeing something fly that you've helped contribute to is a great satisfaction. It's a challenging environment. We get to work with very smart people, and that is part of the joy of what we do.
I'm the kind of person who doesn't like to do the same thing every day. For me, being able to work on something new every few years, I find very exciting.
There's a lot of technical complexity to it in both how we do the test, how we get the data. Often our customers want us to develop a new measurement technique because there's something special or unique about the new engine that we're testing. It's never dull, and we never do the exact same test twice.
I've worked on this program for about 10 years, and it's been a great time. It's been a great journey. And I'm honored to be part of a team that is making supersonic travel quieter and safer.
the camera on the back of your cell phone, blankets that cover firemen, communications devices that are part of everyday society, companies that are, for instance, looking to measure the vibration to great degrees, be part of carbon dioxide or smoke detectors, all based on NASA technology.
We follow the literature, the scientific discoveries that other scientists make, whether it's through experiments or whether we're looking at data that come from other missions, maybe planetary missions and so forth. And then from that, we work with the broader community to understand what is the next question? What is this telling us, and what sort of gaps do we have in our knowledge, and what can we learn if we had the next bit of information? Keeping aware of what's going on, looking at what the next things, proposing some ideas, experiments, getting peer-reviewed thoughts on those, and then going for those things that are most promising. And that's kind of the process we use to go from where we are today to tomorrow.
Istraživački centar Glenn u Ohiju stvara tehnologiju koja će omogućiti sve brže i uspješnije letove u svemir. Okuplja ljude koji su svjesni da je pred njima uzbudljiv cilj, te strastveno i predano rade kako bi ostvarili uspjeh. Zato ne iznenađuje što je NASA zaslužna za toliko revolucionarnih izuma. U posljednjoj epizodi predstavit ćemo još jedan znanstveno-istraživački centar.